Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Acid-catalyzed isomerization of alkenes proceeds via protonation to form the most stable carbocation intermediate, followed by deprotonation to give the thermodynamically most stable alkene. The driving force is conjugation and substitution of the double bond. Moving on to the next step. Compound A is a tricyclic compound containing a decalin-type bicyclic system with a cyclohexene ring. It bears an allyl group, CH2, CH is equal to CH2, attached to a carbon that is allylic to an endocyclic double bond. The terminal double bond, vinyl, is unconjugated with the ring double bond. Moving on to the next step. Traces of H2SO4 protonate the terminal alkene or the ring alkene to generate a carbocation. Through a series of 1, 2 hydride shifts or proton transfers, the double bonds migrate to their most thermodynamically stable positions. The key driving force here is the formation of a conjugated diene system or extended conjugation, which is significantly more stable than isolated double bonds. And for the final step, starting from the allyl side chain, CH to CH is equal to CH2, can isomerase under acid catalysis. The terminal vinyl group migrates inward. Simultaneously, the endocyclic double bond can shift. The net result is that the side chain becomes a propenyl group, CH is equal to CH, CH3, i.e., prop 1N1 vial, that is conjugated with the endocyclic double bond of the ring. This gives a conjugated diene system where the exocyclic double bond is equal to CH to CH3 in trans configuration, is in conjugation with the ring double bond, maximizing thermodynamic stability through conjugation. Option C shows a tricyclic structure where the side chain has become a trans 1 propenyl group, CH is equal to CH3, conjugated with an endocyclic double bond, creating a conjugated system. This is the most thermodynamically stable isomer because 1. The double bonds are conjugated, lower energy, 2. The internal double bond is more substituted, Zaitsev type stability, 3. Trans geometry of the side chain double bond is preferred. Option A shows an exocyclic ethylidene with only a 2-carbon unit on the side, inconsistent with the 3-carbon allyl group in A. The carbon count does not match. Option B shows a vinyl group still present, unconjugated terminal alkene, which is not the thermodynamically favored product. Also, the ring system appears to have gained extra unsaturation inconsistently. Option D shows a fully saturated propyl side chain with no conjugation benefit from the side chain. Acid-catalyzed isomerization would not saturate the side chain, and this represents a necessary loss of conjugation stability. Therefore, the correct answer is C. Therefore, the correct answer is option C.